Today I'm going to talk about hardware accelerated matching of counting regular expressions. So in this XKCD, we have a detective who has a ton of emails in which some addresses are hidden. And it seems hopeless at first, but the Ninja programmer saves the day because he knows regular expressions. So we all know that regular expressions are a part of many string processing tasks, like finding email addresses or like credit card expiration dates formatted in a certain way. But regular expressions also occur in other contexts. So here are some of the data sets which we use in our work to evaluate like what I will talk about next. And there is this field of network intrusion detection. And one example of such a data set is the SNORT data set, in which there are thousands of community maintained regular expression based rules using which they sniff the network packets to see if there is anything suspicious. And similarly, in antivirus softwares, there are the virus signatures, which are basically, or more often, they are regular expressions. And one like freely available such database is ClamAV. It has a bunch of such data, like such regular expressions. And biologists also use regular expressions for their work. In particular, we looked at this set of protein motifs called the ProCite protein motif database. So I would like to talk about matching regular expressions. This is the most standard way of matching regular expressions. You write a backtracking parser, and this is pretty slow because you might have to go over every path in the regular expression. Like if you have something like this, then you might have to like explore all the choices here and all the choices here. So this might take exponential time. But this is actually pretty common in practice. In fact, like some of the very famous regular expression matching libraries like PCRE and grep use this kind of techniques. Also, like the many regular expression matching libraries in languages like Java, JavaScript, Python are based on backtracking. And another technique is, of course, the automata-based technique. You transform the regular expression into an NFA, and then you convert it to a DFA, and then you match the DFA, like you simulate it. And practical implementations tend to use like a bit of both of NFAs and DFAs. As in, if the DFA is like relatively small, it would like fit in memory, it determinizes it. But if it is too big, then it defaults back into simulating the NFA. And some well-known engines which do this are RE2 and Hyperscan. RE2 is like a regular expression matching engine by Google. And there are some nice articles written by a person named Russ Cox about like implementation of regular expression matching engines, which are quite nice. And Hyperscan is some software by Intel. So here is a third possibility in which we have a NFA, and we would like to directly simulate that on what I'm going to call the automata processor. And this idea was first introduced by this paper in 2014 by Lugosz et al. And this is the framework which I will mostly focus on for today. So let's look at this idea in some more detail.
Automata processor is a nice name. So
Yeah.
It's cool. Yeah.
So in the automata processor, we are going to simulate non-determinism directly. And by that, I mean there are multiple active states. And the cool thing about this is that you can compute the transition on all of the active states directly. So regardless of how many active states there are, you compute like the transition on all of them. So every time you get a new character, you just spend O of one time regardless of how many states you have, like as long as they fit in the chip, of course. And here is like a example of like how this basically works, like roughly. Basically, you have this adjacency matrix, and somehow in the hardware you can implement this sort of thing. So like you have like certain active states, and based on this adjacency matrix, which like the hardware literature likes to call the routing matrix, like the next set of active states are determined. So this is like roughly how the automata processor works. And this automata processor has like a throughput of 2.6 gigabits per second, which outperforms x86 CPUs based matching by 256 times, and certain GPU based matchers, which are also based on a lot of parallelism by around 32 times. And it can simulate up to 28,000 NFA states, which is not bad, because it would be like around 1600 different regexes combined together. And for applications like SNOT or like network intrusion detection, often your challenge is to match many regular expressions at once on the packets that are being streamed. So in this case, like this sort of thing is very helpful or could be very helpful. And this adjacency matrix, the routing matrix, is reprogrammable, so you can change it later. So now I will bring in regular expressions with counting. So we have all seen this before. Like if you have lots of repetitions, you could use counting to make them more succinct. And I denote them like this. This basically means that when I have 3 in the braces, this means like it's repeated 3 times. Another example is something like this. So counting makes things more succinct, and counting is also in many, it operates a lot in practice. Around 33% of the SNOT rules and 50% of the pro-side motives had counting. And how do we match regular expressions with counting? So one way is to unfold the counting and then just do whatever we were doing before. But this is not the best idea. In terms of hardware in particular, this will lose the succinctness that you got from the counting, and this means that you need more area in the chip, and also like more energy will be consumed by the hardware. So we want to ask, how can we make this better? How do we make this area smaller, and how can we deal with counting while maintaining some structure about counting instead of just unfolding it? And I will talk about like how we can do that. So here is the automata based framework for that. We have like automata, and I would like to add counters to this. So this is the regular expression below, and for that I have this automata with counting. And here I have the initialization, and I have increments, and I have equality tests. So I add this additional, these are the additional operations that this automata will have. And runs on these kind of automata are as you would expect. So initially you have some initial state, and then based on what character you see, you take a certain transition. And here, for example, like there is this token in this but that state, and the counter has a certain value associated with that token. And this could change when you take this highlighted transition many times. And here you know that this string is accepted. So, but things become more interesting when you have non-determinism. In this particular example, this regular expression refers to the idea that the fourth last letter is an A, and I would imagine the string is over A's and B's. So at some point you have to guess when to take this transition to A, and then you can take 3 more characters at most. So let me illustrate like how this works with a run, and we will identify something interesting. So we have the initial token over here, and because of I see the character A, and then I take that transition as well as this transition, and this is fine for our hardware situation because the hardware is able to have multiple active states. And in this case, I have one token over here and another token over there, and this token has the associated counter value of 1. And now I have 3 tokens, and one of them has a counter. However, when I consume another B, like you take both of these blue transitions, and there are now 2 different tokens which correspond to 2 different values of the counter. So this is what I call counter ambiguity. This corresponds to the situation where you have tokens at the same state, but which correspond to different counter values. So why is this particular situation interesting? Because we were able to simulate non-determinism in our hardware with multiple active states, and using multiple active states corresponds to like having different states in different runs. But if the different runs have different counter values, then we need to represent that somehow as well. However, the challenge is that like if you have a simple hardware counter, it will store only one value at a time. So we need to be aware of this situation. So in this talk, I will talk about mainly 2 things. When can we detect when this situation will arise? And if we can detect that like this situation won't arise, we will take advantage of that. Otherwise, we also need to talk about if that situation doesn't arise, how can we match them more efficiently than unfolding. And this is based on these 2 works. Like one is from PLDI 22 and another is from OOPSLA 23. So this year.
Sorry, are they in your papers or?
Yes, I am involved in the first one, not so much in the second one.
Oh, yeah, but still, oh, the very nice.
Yeah.
Very nice.
I'm not the first author though. But yeah, this is from our lab.
Very nice.
Thank you. So let's talk about how we can detect counter ambiguity. And this algorithm is basically based on converting the counter automata into an ordinary finite state automaton, where you add like the extra component denoting the value of the counter. And this is very much inspired by a regular by an ordinary ambiguity checking algorithm, and I will explain what that means in a moment. So basically, I want to know if it is possible to have 2 different paths in the automaton which lead to the same state but with different counter values. And what I am suggesting is that I construct this NFA which looks like this. So for this particular automaton, the NFA looks like this. Basically, there are these 2 possibilities for the counters to be. And I want to check if there is a path which if there is a path on the same word which goes to the same state but with 2 different values. And to do that, I would basically simulate 2 copies of the automaton at once and check that this is like a very standard ambiguity checking algorithm on standard automaton. So this is why we like call this counter ambiguity partly. So yeah, like if you construct the product of this automaton with itself, it looks like that. And for example, like this state over there, like the ones in gray, those exhibit counter ambiguity because we are able to go to the same state but with different counter values, and those are in a way a witness that if those were the inputs, like that would like exhibit the counter ambiguity situation.
Right?
Yeah.
So sorry. Today, do we have many like audience
There's only James online.
Okay. Yeah. Okay. So here, like, what is the definition of ambiguity for NFA? It is like reaching like any single state by two words.
Yes, that is true. I am using the definition for NF ambiguity a bit loosely.
Okay. Yeah.
But it is
Then
kind
it's
of,
okay. So
related.
yeah. So here like you are using a certain choice of accepting states, right, for the product automaton.
Yes.
And then
So
you are
this acceptance over here is not very important.
Yeah, indeed.
The important thing is like whether you can have like the same first component with two different things in the second component.
Yeah, and then algorithmically you are just solving reachability.
Yeah.
Okay. Yeah.
Thank you.
Thank you.
So
And but then this algorithm, if you do it in a careless manner, then the state space of the state space can be infinite, right?
good point. So yes, but we will always have like this kind of constants, like for example 2 over here. So
Okay.
we don't care about like anything above 2.
Is it the constraint on the formalism? Like, because like I can also imagine like x now like greater than 2 at the end guard condition.
Yeah, so we wouldn't have greater than 2. Well, if you have greater than 2, like then everything greater than 2 is like an equivalence class. But I don't think greater than 2 is necessary. So if you want to count like the exact number of things, like for example, like what you want to check is like something happens exactly twice, you need equality. Another possibility is that you need like you count from 0 to 2, like there is a regular expression r repeated like from 0 to 2 times. So if it is one of these two cases, you can like either use equality or like the less than equal to. But if it is something else, like let's say r m comma n, you can rewrite that as r m times and then 0 to n minus m, if that makes sense.
So then the way I understand it is first, all the NFAs with counters coming from regular expressions with counters, they have some like explicit bounds. I mean, like we wouldn't be talking about constraints like x must be, the counter value must be greater than something. Like we wouldn't have such constraints.
Yeah.
Okay. So that's the first answer. But then the second answer is even if we have such guard conditions, we could use something like region construction for timed automata, after which
nothing so complicated. It's easier than that. Like basically what I'm saying is that if you have like all the kinds of counting constants that happen in regular expressions, like they could be cast down into these two things. One is like exactly so many things, and the other is like 0 to n, something like this. So maybe we can talk about that later, but does that make sense roughly? Like it's like you factor out some part of it and then it can be simplified to something like that.
Right.
Yes, please.
So in this formalism, you start the counter with 1 and then increment up, but you can also, doesn't really matter whether we start with the maximum value and then decrement it to 0.
I guess.
Because that number is just the kind of how many copies you build up the kind of, for instance.
Yes, I think so.
Yeah, so it can be even like 2, 4, 6, 8 or something.
Yeah, maybe. I have not heard about that. but we don't have any kind of comparison between two different counters, so just saying.
Okay.
So those kinds of things don't arise if that's what you're thinking. Shall we continue? So this algorithm is exponential. Oh, because when we unfold, like when this is kind of unfolding, when we do that, like this constant, like for example, the number 2 was probably written in binary, and when you unfold, like this automaton becomes exponentially bigger. This is not horribly bad though, like it's not like we are making it exponentially bigger during matching, because we need to know this fact of whether it's counter ambiguous or not before the matching happens. So this is not as bad as that. And yeah, this is the reason why it's exponential. So here is something about why this algorithm probably needs to be that way. This is NP hard. And here is a reduction from subset sum. So I have these numbers and a target T. And the question is if there is a subset of these numbers adding up to T. And this is known to be an NP hard problem, an NP complete problem, in fact. So I will show that this problem can be encoded in terms of counter ambiguity. So this is kind of a shorthand, but imagine that there is this counter over here, which counts up to N1, and this counter over here, which counts up to N2, and so on. And at the end, there is that counter with B, which counts up to 2. So now imagine that there is indeed such a subset. In that case, you can like make the correct choices in the A's, and you when you arrive at the B with the path on top, you would have consumed only one B, and you would increment the counter, like let's say once. However, if you go through this path, you will have consumed 2 Bs, and then there will be like only 1 B left. I hope I said that right. Like imagine like there are 3 Bs at the end, and T many A's over here. So if you have B, so going through the first path, you will like put 2 Bs over here because you consume only 1. If you go to the second path, you will put 1 B at the end because those 2 Bs are written up by that path. And this is how you can encode like subset sum using this problem. So here is another algorithm which is not exact, but it's over approximating. In practice, it could be helpful. So the idea of this algorithm is that whenever we have a counting constraint, we will just replace that by a regular by an ordinary star, and then we will use the previous algorithm, but now we don't have to do any counting because the countings are gone. And this is like correct only in one way, in the sense that it has false positives but no false negatives. So if you have a run in the original NFA, it will also correspond to a run in the over approximate NFA. However, there might be extra runs in the over approximate NFA which you cannot take in the original NFA because there are certain guards that block that. And the over approximating algorithm is let's say quadratic in size because it doesn't depend on the number n. It only depends on the structure of the automaton. It doesn't depend on the numbers on the transitions. So to summarize this section on counter ambiguity, we showed that this is NP hard. However, generally this is fine because these constants are small, like it's only a few digits, it's not like hundreds of digits. And we have this exact analysis, which is exponential. And this depends on the values which sit on the edges. and it's quadratic on that value rather than the size of the automaton. And we have the over approximate algorithm, which will sometimes gives false positives, but false positives are probably okay because if you think of something as something non-counter ambiguous as counter ambiguous, then you're probably being careful rather than careless. And this algorithm is much faster, and also it doesn't depend on the numbers on the edges. So we went through like some of the data sets which we previously talked about, and many of them have counting constraints. Like for example, in Automata, like around half of them have counting in them. So quite a large number of them do have counting. And we also checked like how many of them are counter ambiguous. So here, for example, in Automata, everything seems counter ambiguous. Part of the reason is because in Automata, every expression begins with a wildcard. So there is like a sigma star at the beginning of the expression, and it could like an unknown number of values which would like lead to different values in the counter. So next we are going to talk about what to do when the expression is actually counter ambiguous. Do you want to ask any questions? Yes.
Oh, thanks. So this table is the result of the exact analysis, right?
Yes.
So your approximation method, like I mean, I think every reviewer would ask like, what's
How many did we miss? Yeah. Overcount.
Yeah, what's the rate of like false positives?
Yeah, I don't have that right now, but I can get back to you on that.
Like, what is your like, I mean, impression? Like, is it in general big? Is this false positive rate big or?
It's generally not that bad, I think.
Then, like, do you have any explanation why? Like the real world regular expressions with counter the.
So one of the things is that there might be certain values like sitting at the, so let's say that there is this counting loop over here, and there might be like some particular character or some state over here which has enough information that makes it not counter ambiguous, so you do not have to go as far as exploring all the possibilities here. Like you just need to look at like what are the entry points into this loop, and that kind of gives you enough information. This is sort of like how I think about this.
And then so I have another question which is quite into the details. Like in the end, you said that yes. Like at the end, you said that with Automata, like so many expressions are counter ambiguous because you had star in the beginning.
Yeah, like sigma star. So it's basically like they have a list of expressions, but the way that we are supposed to work with them is that it's not a matter of membership check exactly, but the question is like, does this pattern occur anywhere in the string? So it's more like, so like translated to like a more textbook kind of regular expression. It's like you have like a wildcard at the beginning, and then the pattern that they care about.
But then I mean, like sigma star, like per se, doesn't have any counter, right? Like it's
yeah
in the like perfect, legitimate and traditional regular expression.
Yeah, it doesn't have any counter, but the issue is that, like, imagine you have a counter right after that, and then you could like throw in so many characters into the sigma star, and that would like increase the counter by depending on like how many things are consumed by the white card.
Can you perhaps write something?
Yeah.
Because okay,
So you have like this, let's say something like this, and then you have like some counter. So maybe this is my string. So I could like feed in this part through this, like through this loop, and then my counter will be increased by this much. Or I could like I could feed in this much, and then my counter will be increased by this much. This is what I mean. So like as this kind of thing can be like is one of the most common reasons why this sort of thing arises. So actually, this was like the example that I had. Like this is basically sigma star, right? Like
so I guess very commonly for this increment operation happens. It comes with the self loop, right? X plus
Yeah.
plus.
Oh yeah, the increment, yeah. That happens like very often. The counting is just on one character. That is true.
Yeah, because otherwise, like you wouldn't probably need this counter, like because you can sort of record the transition by different states, right? So, I mean,
sorry, what did you mean?
yeah, okay, so like, yeah, okay, so it's okay.
But yes, if there are like a number of things in a loop or something like that, then it's like less likely for. I mean, then it's harder for it to become counter ambiguous because then it kind of depends on what is in that sequence of states, etc. Right?
Yeah. Thanks, Anish. Thanks.
Yes.
So regarding this overall approximation, so you approximated A to N with A star, but can we also do the kind of intermediate like A to 5 to A star or A star or A star? So because it's slightly better than A star. I mean,
Yeah, maybe that's a good idea. I have not thought about that.
Intermediate approximation.
Yeah, probably. That's a good suggestion. Thank you. So when we do have expressions with counter ambiguity, we proposed using bit vectors to store the possible values of the counter. And this is almost what it looks like. So here, for example, in this situation, I have two possibilities, 1 and 3, and I will represent them with a bit vector like this, where I have a 1 over here, like this bit is turned on and this bit is turned on, saying that there are tokens with those values. And this is still a better idea because on the chip, like it is better than representing n states. Like this bit vector can probably be like embedded in the chip in a much more succinct way. And one observation is that incrementing these bit vectors is easy. You have to just shift this particular thing to the left. So not incrementing the bit vector, but incrementing all the values at once. So right now, if you have x equal to 1 and x equal to 3, and you wanted to increment both of those, which is what would happen if you took that particular edge in that particular transition, then this is equivalent to shifting the bit vector to the left. So I will talk about this in some more details, but we implemented this idea using spice simulations, and this was like a collaboration with certain electronics people who have like a much better understanding of the architecture of the automata processor. And based on those simulations, we saw some things like this. So, for example, here, like the dashed line is the energy or area which you would get if you unfold it, and on the left we have unfolding versus using just a hardware counter, and we can do that if the expression is unambiguous, because if it's unambiguous, then the counter can take at most one value at a time, and that was the point of doing this. So we could just use one counter, and that would take constant amount of space because it is just a single counter, as we can see from this chart. And if it is counter ambiguous, then we have to resort to using the bit vectors, and there is no asymptotic improvement, of course, but we see that in practice, like we can improve on the energy and area if we used bit vectors instead of unfolding and using so many states. So I would like to talk about the more about the bit vector related ideas in some more details.
Can I, like, what, how come the overhead? Because for, like, at the beginning, the blue is better.
Yes, so it's like another module sort of thing in the hardware. Like there is the chip, and like certain part of it is like certain module. So like there is the routing matrix, which is like the adjacency matrix basically, and then there is this hardware counter which is on a separate thing. So if you add a few more states, it's probably okay. Like it maybe makes the adjacency matrix a bit bigger, but using the hardware counter is like it. I mean, it is bigger than a certain number of states, but it is smaller than like too many states basically.
Oh, okay. So just to make sure, so on the left, in the counter unambiguous part, by this static analysis, you know that you don't need counter, you don't need counters, but
You need a count. You need one counter. Because like the value of the counter matters, but the good thing is that there will be no conflict. So yeah, this is why the overhead is, because like you need to have the counter physically somewhere.
Yeah. So sorry, I'm jet lagged, so I might be asking very stupid questions. But like so on the left and on the right, like implementation wise for your method, right? Red. For your method, implementationally, what is the difference? Or there are no difference on the left and on the right?
Oh yeah, no, there is a difference. So on the left, we know that this is unambiguous.
Right.
So it will never be the case that the counter needs to track two different values simultaneously. So it is safe to use just a single counter. This is why we care about the unambiguity analysis.
Oh, okay, so like a single counter that stores
A single
natural number,
number,
right? A single
like
number.
it's like a single integer basically.
And then on the right, you're using this bit vector
Yes.
counter with
Yeah, so on the right, the bit vector could potentially have like so many different values.
Right.
So depending on the numbers on the edges of the automaton, like the transitions or the size of the counting, that the size of the bit vector has to increase.
Yeah.
For the counter, it doesn't really have to increase unless it's like really large, because it's logarithmic, right? Like so yeah, like for the
Can I, so like now, can you go back to the previous slide? Yeah, okay, so here, like, although so you say bit vectors, but then it's not that you're interpreting this bit vector as a binary code, right? It's just like, like here we are looking at 4 cells, a vector of length 4, and here we are, I mean, like it counts numbers up to only 4. It doesn't count up to 16.
You should think of it as a subset of 4, like subset of 0, 1, 2, 3, 4. Yeah.
And then I guess that in the left case, no, sorry, on the next slide, the left case where there is no counter ambiguity.
Yeah.
In that case, you can use this bit vector of length 4 as a counter that counts up until
16.
Yeah,
exactly.
Oh, yes, it's very
In this particular case, like you don't see that uptick because like the constraints were not so large to see that logarithmic increase. But yes, this is the idea. So we have this logarithmic saving if we can show unambiguity. So this is the point of unambiguity.
Oh,
So does it explain the kind of area difference on the left? So
On the left,
here, because the implementing a counter by a digital circuit is more involved than just a big vector and shift function, because shift, I guess, because the shift is just a register with some network, but the addition, I mean.
are you talking about this overhead like from here to here? Or
Like why the overhead here is smaller than the overhead here is because the counter is more involved, like carrier and the XOR and things like. Well, here you only need the shift and the register, which is much simpler to implement, I guess. Does this explain this difference? Well, but
I hadn't thought about it, but I think you were explaining it right.
the implementation of these vectors.
I mean,
Counters.
I guess like I think you were answering your own question, so
Okay.
I had not thought about this, but yeah, that seems like it. Maybe I don't know. Sorry.
Shinya is a category theoretician who cares about hardware details.
Oh.
Because I graduated in electronics engineering.
Oh, that's pretty cool. I should ask the electronics people. I will clarify with them if this is the case.
Okay, so the final administrative question. So you said that you worked with people who are not only experts of hardware in general, but people who are experts in this automata processor, right? Are they in the?
Yeah, they are experts in automata processor, like, but we are the experts on automata.
Yeah, no. I mean, I just wonder, like, are they in the same university? I mean, like, are they the original authors of the author of the original paper? Or?
I think not. So the original paper was in University of Virginia, from the University of Virginia, yeah. And these people are just in our university.
Oh. So they are experts of automata processor, I mean, consequently, I guess that automata processors are sort of like popular.
I don't know about that. Like this was like the first project we did with them, and as far as I know, this is the first project they have done with the automata processor. Well, not quite. Like they did like one other thing where they improved the amount of area it takes to like represent each state. But I think like it is relatively new to them as well. Like like they may have done like 2 or 3 other things, but not like tons.
Yeah, so I was trying to guess like how popular, I mean, like how big impact this original work on automata processor had. I mean, so and I thought that the impact was so big that in states, in different universities, in like tens or even hundreds of universities, there are like research groups specialized in automata processor.
Probably not that big.
So I can just give some of my thoughts from working in this industry. So I have no idea how big the academic impact is, but it makes a lot of sense to me that someone would build a processor like this, just because as soon as you go near any kind of networking hardware, it's already very specialized hardware. And so having a specialized processor that you could use for all of your filtering rules and all your intrusion detection rules, that makes a whole lot of sense.
Okay, that's great. Good to know.
Yeah.
So one thing I do know is that they probably founded some startup or something like this. It was called Micron. So I don't really know what happened to that because the web page is like gone now. So maybe they stopped working on it.
It doesn't sound too promising.
Yeah, but like I guess they thought that it would have some practical application. So that's all I know. Thank you. Let's look at the next part. So we will talk about certain classes of ambiguous expressions which are somewhat more interesting. And this particular class is called flat, or I call it flat. And some terminology first. So character class is basically like a predicate on the alphabet. It's like a set of characters. So for example, A or B is a character class, and you will often see in practice it's written like this. However, like this is not a character class. This is like the expression AB or BC. Like this is not a character class. And often you will see character classes like this, which is like either A through Z, or W is for white space, or D is for digits. So this is what I mean by character class. And here is what I mean by flat counting, where you have these k many character classes, and they are concatenated, and then you are counting them up to then you have like some counting constraint on them. And this is an interesting case. I will explain why in a minute. Some examples are like this, like here the character class AB is repeated 3 times. So this is just one single thing. And here I have like ABC, which is repeated 3 times, and here is another example. So if you have flat counting sub-expressions, then somewhere in the counting automata, you will have a loop that looks like this. And here is how we can represent that using bit vectors. Like, so with each of the bit, like each of these states might have tokens which have different values of the counter. So with each state, we will assign one bit vector that says like what are the possible, or what are the values that the tokens at that particular state are taking. And so now imagine that a certain character is consumed, and then you have like certain tokens along this loop. So the tokens over here move to here, and the tokens over here move to here, and so on. And when this happens, like let's say that there was some run which was over here, and the value of x was 2 and 4. This basically gets translated to a run which has tokens over here with the same values of x. So what is happening is that the bit vectors are being passed along this loop. They are rotating, and so along this along these edges, like the bit vectors are rotating, and along the back edge, the last bit vector has to be incremented, like because there is this because of the increment in the on the edge, and this can be done by the left shift, as we saw. The interesting thing over here is that all of these operations can be done in O of k time, and k is the number of states over here in that loop, and this wouldn't depend on the values of m and n. So there is one thing which I have not put in the slide, but you do need to check whether this particular expression can be like the bits between m through n, are any of them are true or not. But it is possible to like have a algorithm that like tracks the witness to do this like in constant time, like O of k time. But yeah, so the reason that this is not dependent on m and n is because what are we doing? We are rotating the bit vectors. So that is like some kind of operation along like each of these edges, that's O of k work, and then over here you are incrementing the bit vector by left shifting, but you don't have to do any work that is proportional to m or n. So this is the nice thing about these flat counting sub expressions, if that makes sense.
So you're saying that like naively you have to make this circle n times, at most n times, but you don't have to
No,
do
no.
that. Like
Sorry, so what I mean is okay time, this can be done in okay time per character, is what I mean. Like, so if you have like a new character as input to your stream, you should like compute all the transitions.
so like all of us as bit vectors, and then we just
Yeah.
shift.
Yes, exactly.
Yeah.
And that's it. Like, you don't have to like, so the bit vector itself has n many elements, but you don't have to worry about touching all of them. Yeah. So this is the reason why this particular case is interesting. But the bit vectors are more general than that. So let me explain that in some more detail. Imagine you have two states and transitions which have transitioned into a common state. And let's say that this has counter values like 1 and 4, and this one has 2 and 4. So when they take this transition, you would have a single, you would have counter values of 1, 2, and 4. Like the 2 is coming from 2 and 4 is coming from there, and 1 and 4 is coming from there. So in terms of the bit vector, what is happening is that we are taking like component wise OR. So this is component wise OR. This is not automatically like this might require touching all the elements in the bit vector because we are doing element wise OR. In some hardware ASIC, we could have like some dedicated thing which like does all of this. We have not implemented this, but maybe future work. In software, like if imagine that if this is fits inside a 64-bit register, then this just takes one time, like as long as the number is below 64. Or if you have like some kind of bigger forms of parallelism, then maybe you could like do them together. So we also have a software implementation of these things. So this is mostly the bit vector things, and we have a software implementation of them, and we compared them against PCRE, which is a PCRE, which is the blue line, and it's like written in C, and it's like based on backtracking. And the pink line is RE2. This is also this is Automata based, but both of these use unfolding. And what I have called CA is a counting set automata. Like this is a like the title of the paper is counting set automata, and I have forgotten the name of the authors, but they have like some similar ideas in the sense that like part of what they were doing was to was this idea of doing matching where you do not like where the time per character does not depend on the number of the like the numbers in the counting constraints, which is like a very similar idea to what we talked about. And then the BVA ones are ours. And over here, like what is going on in the x-axis is the value of k is changing, and k is basically this counting constraint over here. And over here, this dot basically is like sigma. And as you can see, we claim that this, regardless of k, this value, this time per character should remain constant. And so I should say what was going on here. So we have the input was like 10 million random A's and B's, and we mashed it on these regular expressions, and this is the total time. And over here, like the k is changing, but in our case, and as well as like the counting set automata in some cases, you can see that the line is flat, indicating that the matching time doesn't really depend on the numbers inside the constraints. So yes. Over here you do not see any of the green lines from CA. So the counting set automata paper supported these expressions, but the techniques they had did not work for this one, so we don't have these ones here.
Do they use also the automata processor or?
No, so all of this is software. This is not this is not about the automata processor actually, but this is about the techniques using the flat counting.
Okay.
So yeah, all of these are flat. So here you have two things. So dot means sigma sigma. It's just how you write regular expressions in languages like Perl or something. And yeah, all of these are flat, so we can use the techniques we talked about in the previous slide. The counting set automata is they don't use bit vectors, but they have a similar idea. Basically, they have somehow if all the values of the counter are contiguous, n through n plus k, something like that, then they just record n and record k, and this is how they save space. It doesn't always work, but it sometimes works and it's pretty good. So I will wrap up.
Sorry, just to make sure that
Okay.
if you can go back to the last, and then then the previous slide. Okay, so this discussion was not directly there in the experimental results, right? Because so,
you mean the this one, software implementation?
yeah. Did you use anything from the last slide?
No, because yeah, we didn't, because all of these are flat. So we didn't need to merge anything.
Yeah. And then even if probably if k is bigger, then this register trick that you mentioned that might not work, but for smaller k, perhaps you get something similar.
Yeah, I think so.
Nice.
It will probably still be better than unfolding, I think. As far as I know, most of the engines just use unfolding. They probably have not thought about the counting related problems, so it will probably still be better if you. So conclusion. So counting constraints are exponentially succinct, and the traditional way to match these kinds of regular expressions is to just convert them into ordinary regular expressions, and this will lose the succinctness. And in terms of chips, this means being more energy intensive and consuming more area. And it could also be slow in case of a hardware implementation, if you have to compute a lot of transitions. In case of a software implementation, my bad. And one of the questions we asked is, if we want to directly simulate counting automata with counters, then when is that simple? And the answer is when we have counter unambiguity. And we also asked this question of what to do if we do not have counter unambiguity, that is, when we have counter ambiguity. And for that, we have we propose using bit vectors, and sometimes asymptotically you can't, they are not necessarily much better, but they could, for example, save you some area or energy. And we also asked this other question of when can you match counting constraints so that the time per item in the stream does not depend on the constraints themselves. And one answer is flat counting. And the general question is open, because there might be many more cases where this is possible, but we were not able to think of them. So thank you. I am happy to take more questions.
Any questions?
Hi, this
Hello.
is Jay.
Hi, GA.
Hi. Yeah, I joined this talk. Sorry, I joined this talk in middle. So I have maybe another question about the regular expression matching. So is there any method to return? Yeah, one is how many matching situations. Matching situations. What I mean is that given you a string and a
Yes.
regular expression, can you return how many different kinds of matching?
Like how many substrings match the expression?
Yeah. I mean, given a string and a regular expression,
Yeah.
there may be a different ways to match the string, right?
Yes.
And so, how many? Yeah, the question one is how many different kinds of matchings? Is there any method, very quick method to return?
So I would imagine not, because well, I'm not sure, but seems like there could be exponentially many. But one interesting thing I could point you towards is like I like to call this regex matching disambiguation. So for example, if you look at parallel style regexes and POSIX style regexes, they have like they are not asking the membership question, but they are asking like whether there is a substring. And parallel regexes and POSIX regexes, they have different rules for what they prefer to match.
Mhm.
And one of them is like based on choosing like the left choice always and like the maximum number of iterations of star, and the other one is like the longest match that you can find. So but like these are two common strategies for substring matching, but I could imagine that there are much more. But as for the question of like how many matches are there, I am not sure. It does not seem like it can be done pretty fast. But
So the further question is that if they have this method, and then how to return in the position of the, I mean, if for example, for every atom or the symbol in the regular expression, and we each of them have, for example, we give them a position, and then and then the second step is we return the position sequence, how they match the string or something.
basically, a more general version of this question is like figuring out the parse tree for the regex. I don't know a lot about this, but one of the popular choices for like choosing a parse tree is this greedy strategy. And I think it can be done like in linear time for the regex. Probably even if you have counting, I am not sure. Like
Okay.
But if the question is like how you can enumerate all parse trees, I am not sure about this.
Okay. Thank you.
Yeah, thank you. Great questions.
Any other questions?
So I have a high level one. I'm actually coming at this not from research, but from teaching. So I often end up teaching kind of the foundations course where students see finite automata and regular expressions. And I really liked your motivation section where you talked about some of these big data sets of regular expressions. And so one thing I was wondering, beyond just, giving them those statistics that are already in your intro slides, if I'm going to my students and trying to convince them to care about regular expressions, which is hard on some days, what would I want to show them that you've seen, just to show them kind of some of the impressive applications of regex that are out there? You made me care about regular expressions, so how do I make other people care about regular expressions?
That's a good question. I don't know.
Well, I'll have to read your paper.
I don't know if that will help, but you are certainly welcome to.
You can't stop me.
So I don't know if this answers your question, but like one thing I found useful is that there are websites like regex 101, and they have like a community section or something where you can like sort by upvoted, and then you get like a list of regular expressions.
Oh, that's great, actually.
It's kind of interesting to know.
Yeah, and I think for students, seeing something that someone else there out in the world decided they cared about versus something that's just in the book, I think that's nice. Thank you.
Maybe you can tell them about session types.
I they will hear about session types.
Session types.
She is the expert on that.
I'm not the expert on session types.
But I am certainly.
Yeah, sure. Thanks. So in the beginning, you said so first of all, like you gave some like no, sorry. So in the beginning, when you introduced automata processor, you said it is ASIC, yeah, ASIC, right? But then you also said that some part of the circuit is reprogrammable. For example, in the network, like intrusion detection application, you can add new rules.
So I imagine that you can reprogram the adjacency matrix, and by doing this, you can like refresh the memory and like reload the thing with a new set of regular expressions. So is this what you're asking?
Oh yeah, exactly. Because like to me, like I'm no expert in hardware, so I thought that anything reprogrammable would fall into the category of FPGA.
Yes. So there is a bunch of work matching regular expressions with FPGA actually. I think like some of the ideas would also apply, but probably ASICs would be like much faster, I think. I am not sure. I have not thought a lot about FPGAs. I am not an expert. Thank you.
Then the final comment is I don't know whether you have talked to Hiroya, but Hiroya is an expert on the riddles.
Riddles, okay.
Yeah. So, and I wonder, like probably like not a direct connection, but I wonder like what possible connections there are between your work and his. So, like I don't know, like riddles, like regular expression denial of service.
Oh, okay, I see. I thought like you were talking about like the kind of thing that troll asks you when you try to cross the bridge.
Riddles.
Yeah. Riddles.
Yeah, I understand now.
Yeah.
So I have like I'm not an expert on that, but I have certainly heard of that because a lot of these engines are like backtracking based. Like I think like the RDOS people kind of try to take advantage of that because it's easy to like not easy, but like it's possible to like throw them into a loop or something. Like they have this term called catastrophic backtracking. So that is like certainly a good motivation to not use backtracking, but use automata based methods. But
so actually, I have a question just for context. So I understand the catastrophic backtracking, but when you talk about regular expressions and denial of service, what's hard for me to understand, like, where are the opportunities for an attacker to input a regular expression as an attack?
I think they input strings, right?
Oh, I see. That makes more sense. Thank you.
And so one of the like related but not super related, one of the advantages of having backtracking based engines though is like one of them is easier to program, and like there are certain constructs which are like easily implemented in backtracking based engines, like for example look aheads and things like that, which are there in like this NOR dataset, for example, like which we just threw out when we did these experiments. But if you use like a backtracking based engine, it's possible to like match those. So that's good. And also maybe things like back references, which are like not actually regular, but you have like depending on how the backtracking engine is implemented, like sometimes you could match those as well.
Yeah. So one thing that this is making me think, both in terms of the denial of service attacks and also the fact that you have your exponential algorithm, you have a much faster approximate algorithm. All of this makes me think there would be a lot of value in designing sort of multi-pass regex matchers that, you know, try the fast approximate thing first and then go to do the more complex exponential check. In particular, you know, I know not the back references are a really important thing, but also capture groups, I feel, are also much clearer how to implement when you're doing a backtracking approach. And so I could see a lot of value in an algorithm that does an NFA or DFA based approach to check whether you match the expression at all. And then once you find, you know, the one packet out of a billion that actually matches, then you go back and you run the exponential algorithm to actually extract the capture groups.
Yeah, I see.
Just a thought.
Any other questions?
Yeah, I have some questions. So maybe you answered this when answering GA, and I didn't understand, but so you basically talked about matching from the beginning of the string. Is that right?
Yes. So generally, I am thinking of like the membership problem rather than like figuring out which substring matches.
And so if you so obviously, yeah, so a normal regex engine will try and match anywhere in this string. And I'm just wondering, is any of the work done reused as it discards the first character?
So one way to why does it discard the first character?
So like you match from the beginning of the string and then you don't match, and so then you sort of discard the first character and then.
Oh, okay. Oh,
Right.
One way to do this in a more streamlined manner would be to add like a wildcard to the beginning of the expression. And like if you add like sigma star to the beginning of the expression, this will let you ask the question whether there is any match in the string at all.
I see. Yeah, I see.
So actually you can use this to extract the match. Basically, you have to like add the sigma, like, I mean, assuming that you can do multiple passes, you can do the following. You can add sigma star to the beginning of the regex, and then you ask this question of whether there is any prefix which matches, which contains a match, and then you reverse the regex and like go backwards to see if like what was the match.
I see.
So I think that should work.
So then you talked about this bit vector in the ambiguous case. So is it unbounded?
No, not if it's in the hardware, and probably also not if it's in the software. It is not anyway. It's not unbounded. You can always bound it using like these m and n, right? So
I don't get that, but
so what?
Like, can't you just like while you're evaluating it, you sort of spawn new tokens, right?
Yes. Are you asking if I pre-allocate the bit vector to the maximum extent necessary?
I'm just asking if you can bound it. So you can statically
Yes.
bound the length of the vector. Okay.
Yes, we can bound it because we know what is the maximum number of counting we need to do.
I
So
see.
yeah, we can. That is the bound basically.
Okay, great. Okay. And then I guess my last question is, so pretty much any regex implementation has all these fancy features which aren't part of like the academic definition.
Yeah.
So the examples that you gave of your large regex libraries,
Yes.
so you were
But
able to actually process all of those because they didn't contain
No,
these
no,
fancy features?
they had like a lot of those things which we couldn't support, like back references, look aheads,
I see.
capture group, like yeah, lots of those things. So yeah, we had to throw those away.
Like, can you give some number there of how much you could process?
I'm sorry, I don't remember. I can get back to you on that.
Okay. But there is at least some substantial amount that you
Yeah,
can process. Okay, that's
yeah,
cool. All right,
that is
thanks a lot.
Yeah, thank you.
Okay, I have one very quick question, I hope.
Please.
On the results, like experimental results of your algorithms, there's one of them that looked strange to me. Can you go back to the slide? I mean, there's obviously a line that's very much below all the others. On experiment C, the BVA OPT, like, do you have any explanation of why this is taking so much,
So
like,
little
so
time.
little time?
Um,
Is there something special about this regular expression?
I'm not actually sure.
Okay, that's fair enough.
What is this indexing? Like, it has to be at least k characters. It could
Yes.
also be more.
Yes.
Okay.
Any final questions? Yeah, then let's thank Agnisho again.
Thank you.
Very nice. Oh, thanks a lot. Yeah, great talk. Thank you.